lesson is over finding real roots of polynomials. So these are where the function really crosses the x-axis. These are the real roots of polynomials. And the first method that I'm going to talk about is when you can solve by factoring. So in this first example, looking at this equation right here, which I've already replaced f of x with 0, or I've replaced y with 0 because that's what I'm looking for, my x-intercepts, and those are where y is 0. So I replace y with 0. In this first example, you are able to factor the polynomial. So let's write that. You are able to factor the polynomial. In this type of example, we notice that when we have this polynomial right here, I can factor it. I can absolutely take out a GCF. And I want to do that first every single time if I can. Always take out a GCF first. So what's my GCF? Between 2x to the fourth, 2x cubed, or negative 2x cubed, negative 24x squared, I can factor out a 2x squared. When I factor out a 2x squared, I'm dividing that out of each term. So 2x to the fourth divided by 2x squared, I'm left with x squared. Moving on to our next term, when I divide that out, I'm left with negative x. Negative 24x squared, when I divide out a 2x squared, I'm left with negative 12. And now what's left is I have a quadratic trinomial, which I can also factor. In this particular, what's inside those parentheses, I need two numbers that multiply to negative 12 that have a sum of negative 1. Those signs are going to be opposite, and we're really subtracting to negative 1, and our numbers are negative 4 and positive 3. So when I factor this, I write my GCF, and I factor it as x minus 4 times x plus 3. And now we have our polynomial in factor form, or intercept form. And what do you do to find the intercepts? You set each factor equal to 0, and you solve for x. So I'm going to set 2x squared equal to 0. I'm going to set x minus 4 equal to 0. And I'm going to set x plus 3 equal to 0. And when I solve that, each one, I get x squared equals 0 right here, which is just x equals 0. When I solve this second one, I get x equals 4. When I solve this third one, I get x equals negative 3. So these are the three real roots of the polynomial. And right here, you can see this 2x squared equals 0. We've talked about graphing polynomials. It has a multiplicity of 2, which means what is it going to do with this root right here? It's going to bounce off of it, right, and end in the same direction. But we just need our real roots of our polynomials, so we're going to write it. We're going to list them out. And how do we list? We use roster notation, so those squiggly little brackets. Negative 3, 0, and 4. Those are the roots of this polynomial. Let's move on to example number 2. In this second example right here, we look at it, x cubed plus x squared minus 20x minus 96. When I see a 4-term polynomial, I think, all right, I'm going to factor by grouping. Well, I can't do that in this case. So I'm not able to factor this particular one, but I'm given a little piece of information right here. X equals 4 is a root. So in this particular problem, you're unable to factor the polynomial, and let's write this out. You are unable to factor the polynomial but you're given a root or a factor. And in some cases, you're given multiple roots, like x equals 4 is a root, x equals 3 is a root. Sometimes you're given a factor. X plus 4 is a factor of the polynomial. So what we're going to do when we're given this particular polynomial, this function, and we're given the fact that x equals 4 is a root, I'm going to use synthetic division to divide the factor out of the polynomial, okay, or to divide that root. So how do I use synthetic division? I'm going to take that root, And I'm going to go ahead and write here, if 4 is a root, then x minus 4 is a factor. So let's write that out, because if I had said x minus 4 is a factor, well, that's different. What we're going to do is take the root and we're going to divide the root out. So if x minus 4 is a factor, you're going to divide out a positive 4. So let's use synthetic division. I put my coefficients here, 1, 7, negative 20, and negative 96. And what do? Synthetic division, I bring down the 1. 1 times 4 is 4, and I add. 7 plus 4 is 11. Now I multiply 11 times 4, and I get 44. Then I'm going to add negative 20 and 44. I get positive 24. 24 times 4 is positive 96. I get 0 as my remainder. This is really important. If you did not get 0 as a remainder when you use synthetic division, that means x equals 4 isn't a root, which means x minus 4 isn't a factor. But this particular problem tells you that x equals 4 is a root, so you absolutely should get a remainder of 0. But let's write that out so we have it in our notes. Remainder is 0 if x minus 4 is a factor. Or if x equals 4 is a root, however you want to look at it. So now let's write this out. What are we left with? Well, we're left with this equation right here. X squared plus 11x plus 24. And I've set that equal to 0, and I know x minus 4 is a factor already, so I've already factored out that particular factor. But I've got this remaining trinomial that I can actually factor. I need two numbers that multiply to 24 that add to 11. What are those numbers? 8 and 3. So I'm going to write out my factors. They're both positive, so x plus 8 times x plus 3, and then x minus 4, which we already know is a factor. So what do I do when I've got it in factor form? I set each factor equal to 0, and I solve for x. And we already know this one is, but I'm going to go ahead and write it out so you have it. So we get, in this first particular equation, x equals negative 8. For this next root, x equals negative 3. And the last one, which we already know, is x equals 4. So let's list out our roots for this polynomial, and let's list them all out. You don't have to, but I'm going to. Negative 8, negative 3, and positive 4. So I've got all the roots. So, in this particular problem, it might say, find the remaining roots, which you wouldn't need to write that x equals 4 because we already know that that's a root of this equation, or of this polynomial. So those are two examples where you can factor. And if the second example was we couldn't factor it initially, but we were given a little bit of information. We used synthetic division, and then we factored. Okay, so the first one we just factored. The second one we used synthetic division, and then we factored. And then in this next method, we're going to solve using the quadratic formula. So polynomial functions may also have irrational roots, right? So what do we know about rational numbers? We know that rational numbers are any number that can be written as a rational or as a fraction. Okay, well, what are irrational roots? Those are those roots that might contain a square root of a number that is not a perfect square. Okay, so you might have that. Or you'll have decimals that never, ever, ever end and never, ever, ever repeat, which are these right here, right? The square root of 32, if I converted it to a decimal, it never ends and it never repeats. So in this next particular problem, we can't factor it. We are given a little bit of information, though. X equals 1 is a root. Okay, what do we know to do? We're going to divide that root out. So I'm going to take out 1. Now, if it said x minus 1 is a factor, then x equals 1 is a root, and the root goes here, okay? So what goes in there. We put our coefficients in there, 1, 2, -8, and 5. And then how do I use synthetic division? Bring down the 1. 1 times 1 is 1. And then I add. 2 plus 1 is 3. And now I'm back to multiplying. 3 times 1, right? I just keep multiplying it by that. 3 times 1 is 3. And then I add. -8 plus 3 is -5. Now I'm going to multiply again. -5 times 1 is -5. And I add and get 0 as my remainder. Again, that remainder is 0, which confirms x equals 1 is a root. If you were ever given a problem that said, is this a root? And you can use synthetic division out. If you get a remainder, it is not a root. Okay, not a root if you get a remainder other than 0. So now what are we left with? We are left with this quadratic right here, x squared plus 3x minus 5. We've got this quadratic, and if you want, you can write x minus 1 here. But this right here is not factorable. I can't think of any numbers that I can multiply to get -5 and also add to get +3. So in the case where you cannot factor your quadratic, what can you use? You can use the quadratic formula. So quadratic formula, in this particular case, a equals 1, b equals 3, and c equals -5. And then you're going to plug them into your quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And then we're just going to simplify it as we walk down. So let's simplify our discriminant first. So I get -3 plus or minus the square root of 3 squared is 9. -4 times 1 times -5 is +20 over 2. And then we're just going to simplify a little bit at a time, which is x equals -3 plus or minus the square root of 9 plus 20 is 29 over 2. And I actually cannot simplify this further, which means that's my answer. Okay, and I've got 2 remaining roots, -3 plus the square root of 29 divided by 2, -3 minus the square root of 29 divided by 2. So these are the remaining zeros. And you can leave it just like that. I do want to point out that if you have a number underneath your radical symbol, right, your radicand, if your radicands can be simplified, you know, like you do have the square root of 32, right, simplify it, right? How do I simplify that? Well, that's the square root of 16 times the square root of 2, which is 4 square roots of 2. So make sure you simplify what's underneath your radical when you're using your quadratic formula. Okay, let's move on. The very last little bit, which is a lot of work, but I'm going to show it to you. Let's say you can't factor it. Let's say you don't have any additional information. The only thing you can use is the rational root theorem, which is a little annoying, but I'm going to show you the process. It's not annoying. It's just really long. So not all polynomials are factorable. When this is the case, we can use the rational root theorem to determine all possible roots of the polynomial. So that's what this will do. And rather than read you this, I'm just going to show you what to do because it's a lot of, it'll help if I show you, okay? It makes a little more sense. So what are the possible rational roots of the polynomial? So that's all we're finding. What are all the possible roots? The first thing we're going to do is identify the constant term and the leading coefficient. This is our constant term, -6. I'm going to call it P. This is our leading coefficient. I'm going to call it Q. That's our leading coefficient, which is 2. We're going to find the factors of the constant term and find all the factors of the leading coefficient. So the first thing I'm going to do is find the factors of 6. What are the factors of 6? 1, 2, 3, and 6. Then I'm going to find the factors of 2. So we're just listing out the factors. Factors of 2 are 1, and 2. I'm going to change colors here. Then you're going to write all the possible rational roots by writing each factor of the constant over each factor of the leading coefficient. So here are the possible factors. The possible factors, and you might see it as positive or negative p over q. So what I'm going to do is I'm going to take each factor of 6 and I'm going to put it over each factor of 2. So watch how I do this. And everything is positive or negative, right? Positive or negative, every single number I write. Positive or negative, 1 over 1. Positive or negative, 2 over 1. Okay. Positive or negative, 3 over 1. Positive or negative, 6 over 1. Now we got to move on and put all of those numbers over 2. Positive or negative 1 over 2. Positive or negative 2 over 2. Positive or negative 3 over 2. Positive or negative 6 over 2. So those are all the possible roots, but you might notice that we have some repeaters. So let's delete those. We have positive or negative, and I'll write these out. Positive or negative, we have 1 right here. We have 2 as our next one. We have 3 as the next one. We have 6 as the next one. We have 1/2 as the next one. And then 2 over 2 is just 1, and we've already got that listed, so we don't need to write that again. Positive or negative 3 over 2. Positive or negative 6 over 2, which is just 3, and we've already got that listed as well, so we can cross that out. So these are all the possible roots of this polynomial. So we've canceled our repeating values. The next thing we're going to do is, you might encounter questions that just say, what are all the possible roots? Well, here's all your possible roots right here. But it might say, what are the actual roots of the polynomial? And in this case, you have to plug each one in for x and determine the value of y. So I'm going to show you how to do that. Let's find f of positive 1. When I plug positive 1 in for x, right there, and right there, I get 2 times 1 cubed plus 9 times 1 squared, right? I'm just evaluating for f of 1, plus 7 times 1, minus 6. And if you want to pause the video and figure that out right now, go ahead and do that. I've already done it. F of 1 is 12. In this case, we're looking for our roots. The roots are your x-intercepts. X-intercepts are where y is 0. If I plug in 1 for x, do I get a 0 value for y? No, I don't. So 1 is not a root. We move on to the next one. Now we're going to plug in negative 1. So now I'm going to plug in 2 times negative 1 cubed plus 9 times negative 1 squared plus 7 times negative 1 minus 6. You can pause the video and work this out now. F of negative 1 is negative 6, also not a root. So what I would encourage you to do is pause the video and plug in all of these values in for x and see which ones you get an output of 0 for y. So when I plug in, I've already done 1. When I plug in 2 for x, f of 2 is 60. That is not a root. F of negative 2, when I plug in negative 2 for x, I get 0 for y. This is a root. Negative 2 is a root because when I plug in negative 2 for x, I get a 0 value for y. Now we can plug in 3. F of 3 equals 150. That's a no. F of negative 3, when I plug in negative 3 for x, I get 0 for y. That is a factor. That is a root. Negative 3 is a root. I can keep moving on. One of the things, I'll just keep moving on. And I'll plug in f of 6. I'll plug in 6 for x. I get 792, which means 6 is not a root. If I plug in -6, I get -156, not a root. If I plug in 1/2 for x, f of 1/2, I get 0 for y. So 1/2 is a root. Now, one of the things I want to point out is that this function is a cubic function, right? 2x cubed, which means I'm only going to have a maximum of 3 roots. I don't need to continue. My roots in this case are -3, -2, and +1/2. You could even write out your factors are x plus 3. Your factors are x plus 3, x plus 2, and x, did I write that right? And x minus 1/2. X minus 1/2, obviously, I can write it differently. I can write it as 2x minus 1. But that concludes your notes. This rational root theorem takes a really long time, but that concludes your notes over finding real roots of polynomials. I hope it was helpful.